Okay, well, let's start talking about amines. So, amines are interesting compounds, somewhat similar to alcohols, but they're found in a wide variety of molecules. Here you can see some interesting amines, morphine, atropine. But before we get into that, let's just talk about which sections we'll cover. So, we'll talk about amines. This is our last section of nomenclature. We'll look at properties of amines, and then ways that we can prepare amines. So preparations of amines. What's nice about this chapter is lots of it is review. In fact, there's only a few things that are actually new, and those are mainly down here in the last section. Everything else is based on things that we have seen before. So why this chapter? Well, a lot of it is due to the abundance of nitrogen and the amine functional group in natural products. In fact, natural products that contain amine that tend to be plant-derived and have physiological action are referred to as alkaloids. And some of these alkaloids are morphine, cocaine, and nicotine. In our body, we have several amines that are hormones, such as adrenaline, noradrenaline, and dopamine. So amines are really the last functional group that we'll talk about, and they're very important biologically. So as mentioned, alkaloids tend to be molecules that have these amines in there and be biologically active. So atropine is isolated from the deadly nightshade plant, and if you take it, it tends to cause your pupils to dilate, which is mydriasis. And ladies used to think this was beautiful back in, I don't know, 17, 1800s. And so they would actually take some atropine and it would dilate their pupils and they would then consider themselves beautiful. Nicotine, of course, is found in tobacco, and conine is found in hemlock. This is how they killed Socrates. They made him drink hemlock and he died. Anyway, so some interesting molecules there. So let's talk about naming amines. Before we get into that, just some general ways to classify and categorize amines. We've talked about alcohols before in categorizing them, and we categorize the alcohol based on the number of carbons the alcohol carbon was attached to. So in this case, that was referred to as a primary alcohol. That's a secondary alcohol, and tert-butyl would be a tertiary alcohol. Now, it's a little bit different for amines. It's not the number of carbons the nitrogen carbon is attached to, but how many carbons are actually attached to the nitrogen. So a little bit different way of classifying amines. And so you can see an example of a tertiary amine compared to a tertiary alcohol. Now, the reason we don't classify them the same is we really couldn't have a tertiary alcohol. Of course, alcohols only typically have 2 bonds, and if they had 3 bonds, they would be a positive. And even a secondary alcohol is no longer an alcohol. It is an ether. So we've talked about this before, but really what makes an alcohol is having an H off of that oxygen. So when we categorize alcohols, we base them off of the carbon that the alcohol is attached to and how many carbons are attached to the carbon that then has the alcohol. When we classify amines, we classify it by the number of carbons actually attached to that nitrogen. And so what defines a alcohol is having an H off of that OH connected to an sp3 carbon. What defines an amine actually is the lone pair. So in tertiary amines, we have a lone pair. In primary amines, we have a lone pair. And so again, for amines, you classify them based on the number of carbons attached to that nitrogen. And if we don't have a lone pair, they're no longer referred to as amines. They're now referred to as ammoniums. And so this is what would be referred to as an ammonium salt. Okay, so in nomenclature, there's actually several different ways that are IUPAC accepted. And so we can name them, if they're simple, just by naming the alkyl group with the YL followed by the word amine. As you can see here, we have a methyl group with an amine, so we call that methylamine. Here we have an ethyl group with an amine, we call that an ethylamine. Here we have an isobutyl group with an amine, so isobutylamine, and cyclohexylamine. For the IUPAC systematic way of naming it, we drop the E and replace it with amine. So essentially it's just like alcohols. In alcohols, we drop the E and add OL. In this case, we drop the E and add amine. So down at the bottom, you can see how we would name an amine. 4,6-dimethyl-2-heptanamine. If we replace that amine with an OH, it would be 4,6-2-heptanol. So all for alcohols, amines for amines. Now the question comes, well, who has higher priority? And we've talked about this before. The more oxidized you are, the higher priority. So carboxylic acids have higher priority than alcohols, and alcohols have higher priority than amines. So if we have an amine and a higher prioritized functional group, the amine is now named as an amino. And it's a substituent, so it's named out in front. Of course, the higher priority functional group gets the lowest number. So the correct name for this should be 4-amino-butan-1-ol. We'd need to indicate where the alcohol is. And so again, if the amine is subordinate or a substituent, it becomes an amino group, and then you name the higher priority functionalized group. Like in the next example over, that is an amino benzoic acid. The benzoic acid has the higher priority functional group. So you can name that as para-aminobenzoic acid, p-aminobenzoic acid, or 4-aminobenzoic acid. Like I said, a lot of this chapter is review. So we've already talked about aromatic rings with nitrogens off there, and they're referred to as anilines. And so we can actually use the aniline as the base name. So if we have a nitrogen off the ring, we can refer to it as an aniline, and the next molecule over, we would refer to this as a chloroaniline, specifically a metachloral aniline or a 3-chloroaniline. And then if we have multiple substituents off there, again, the aniline would get the lowest. We would count to find the next substituent, arrange them alphabetically. So it's 5-ethyl-2-fluoroaniline. So again, if we have multiple functional groups on there, we need to understand which one is higher priority. So you can actually look in your book at the back. In the appendix, I'll look it up right now. It's Appendix A. Appendix A gives you a list of all the functional groups and their prioritization. So really amines are at the bottom of the list. So then it goes alcohols, ketones, aldehyde, nitriles, amides, acid halides, esters, and carboxylic acids. So in this case here, we have a alcohol which has priority, and so this molecule would be 2-aminoethanol. Here we've got a carboxylic acid, so we would name it as a carboxylic acid. It's 3 carbons, so it's going to be a propanoic acid. So it would be a 3-amino propanoic acid. Okay, so down here we've got a carboxylic acid. So this is 4 carbon, so that's a butanoic acid, and this simply becomes a substituent. So imagine if it was a bromine or a methyl. If it was a bromine, it'd be 2-bromobutanoic acid. If it was a methyl, it'd be 2-aminobutanoic acid. And over here, we've actually got 2 nitrogens. So you might be tempted to name this as an aniline, but the higher priority is going to be a carboxylic acid. So this is known as 2,4-diaminobenzoic acid. Here we've got a ketone that's higher priority, so we number to give it the lowest number. And again, this becomes an amino substituent, 4-amino-2-butanone. So in this case here, we have aniline. And here we have an aniline with a carbon off of it. And so you may wonder if you should call this toluene or a aniline. In fact, this actually has its own name. These are known as toluidines and anisidines. Okay, but you can always name them as 4-methylbenzeneamine. So again, drop the E and add amine. That would be the IUPAC way to name this. But notice this guy over here, N-methylaniline. So we can have more than just one group attached to the nitrogen. So far, we've just looked at primary amines. This would be considered a secondary amine. And so then the question comes up, well, how do we name secondary amines? And here we have lots of different options. So if they're just simple, okay, having issues with technology as usual. So down at the bottom, I was just going over the aromatic amine. So this is known as an aniline. Notice this one here is N-methylaniline. And again, here we've got a amine and a methyl group. So you may wonder if you want to call that a toluene. In fact, this has a different name, as I mentioned, toluidine. So when I was talking about the secondary amine, I was talking about this molecule here. And so far we've only been naming primary amines. So let's talk about naming secondary and tertiary amines. And this may already be familiar to you because this is how we named amides. We indicate that the substituent is off of the amide by putting the prefix of N. That's one way to do it. There is another way of doing it, and it's like naming ethers, where we simply name the groups around the amine and append amine at the end. So in this example right here, we alphabetize and the groups. So around that amine, we have an ethyl, methyl, and a propyl. So we call it ethyl methyl propyl amine, just as if we had a ethyl propyl ether. So we would just say ethyl propyl ether. Sorry, having problems again. Okay, I don't know what the issue is. Maybe my computer's caught a virus. Ha 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 ha. So, as I was mentioning, just like we name ethers, we could have an ethyl propyl ether, and so we can do the same with amines. If they're simple alkyl groups, we can just name it that way. So like this ether here would be referred to as diethyl ether. If it's an amine, it's diethylamine, and at the end, trimethylamine. So that is accepted. There is another way, and that is to find the longest continuing chain. And this is very important when you have very complex molecules, such as this one in the bottom right. Now this one right here, let's draw it out so you can see it. It's got 3 ethyl groups around it. So we could just name it by the simple way, triethylamine, Or the IUPAC way is to find the longest continuing chain, which in this case would just be 2 carbons, and we're going to name it as an ethanamine. And then what we do is we name the substituents off the nitrogen and put them out front with an N for each of the substituents. So in this case, it would be an NN-diethyl ethanamine or triethylamine. Either one of those works. In the next case below, we find the longest chain, which is going to be 3. So that's going to be a propanamine. And then we put out front the groups that are off of the nitrogen. And off of the nitrogen, we also have an ethyl group and we have a methyl group. So N-ethyl and methyl 1-propanamine. Or, in this case, ethyl-methyl-propylamine. Now, as I said, the box to the right is actually a lot more complex. There's no way that you're going to get by using simple nomenclature on this. There's no way to give this group right here in the yellow box a simple name. We can say methyl ethyl, but there's no simple name for that. So we have to go to the systematic way, which is find the longest continuing chain, which in this case is 6. We're going to number in the direction to give the amine the lowest possible number, which is 3. And then what we're going to do is arrange it so that all the substituents are listed alphabetically. And so the N's being italicized don't count in the alphabetization. And so what we're going to alphabetize by is the C and the E and the M. Of course, there's some stereochemistry there. So if we look at this molecule here, there's 6 carbons. It's going to be a hexanamine. We need to indicate where the amine is on that 6 carbon chain. It's at the 3 position. And then we need to list all the substituents. So at the parent chain, we have a 2 chlorine groups, so 2,2-dichloro, and then off of the nitrogen. Now we're not going to put numbers, but we indicate off of the nitrogen by having that italicized N, so N-ethyl and N-methyl. And of course, if there's stereochemistry, we want to indicate that. So again, a couple ways to name them. We can name them in the systematic way, which is to find the longest continuing chain, drop the E and add amine, make sure that you indicate where the amine's located. So in this case here, we have the amine and a pentyl group. So we could just say pentylamine. We wanted to use a systematic, we would say 1-pentanamine. The next example over, we could just name the alkyl groups. So on one side, we've got a butyl, on the other side, we've got an ethyl, and so we could call this butyl ethylamine. Or the longest chain would actually be the butane. The amine is connected at carbon 1, so that would be a 1-butanamine. And then we would indicate that off of the nitrogen, we have an ethyl, so N-ethyl. And neither of those are accepted. And finally, this last example, we have an ethyl and a methyl and a propyl, so we could call it ethyl-methyl-propylamine, or we find the longest chain, which in this case would be the propyl. And the nitrogen's connected at position 1, so that would be a 1-propanamine. And then if we call it 1-propanamine, the other substituents are an N-ethyl and an N-methyl 1-propanamine. Okay, so you can look at this example at the bottom here. There's no way to name this guy here with the simple common name. So we actually have to find the longest carbon chain, which is going to be 7. So this is going to be a heptanamine. Specifically, it's going to have a 3-heptanamine, meaning that the amine is located at position 3. The other substituents that we have is a 6-methyl group and an N-ethyl. So in the end, this would be called N-ethyl 6-methyl-3-heptanamine. Okay, thank goodness. That's the last of the nomenclature that you'll have to see, unless you want to do this again. So let's talk about the properties of amines. As I said, amines are characterized by having a lone pair of electrons on a nitrogen that has sp3 carbons attached to it. Now in this top right here, if we look, we can actually see that this adopts kind of a pyramidal shape. The overall electronic geometry of this is tetrahedral. The molecular geometry would be pyramidal. Those lone pairs are actually found in an sp3 orbital and tend to be very basic or function as a nucleophile. And so we can see amines, and we have seen amines act as bases, and they will pull protons off of acidic molecules and they become protonated. And in this case here, when they become protonated, they become ammonium ions. No longer amines because they no longer have a lone pair. We can also do SN2 reactions with amines. Those happen best on methyl and primary alkyl halides, and we can end up with a quaternary ammonium ion as well. So that nitrogen has a region of high electron density. Now you may remember from Gen Chem that we always said that the amines deviated from the ideal bond angle of 109.5 due to the lone pairs taking up more space. And so everyone memorized that the bond angle is 107, but that bond angle of 107 is only true for ammonia. As we saw with ethers, that bond angle actually spreads out as we get alkyl groups substituted on there. And so when we have methyl groups around there, that bond becomes more like a typical bond angle and becomes closer to 108. And if we happen to include some more bulk off of here, it would get closer and closer to 109. And it actually may be larger. If we had terp-butyl groups here, that bond angle actually may be larger than 109 and actually may be around 110 or 111. So it's not always true that the bond angle around nitrogen is 107. It's 107 when you've got small hydrogens here and a large electron cloud. But if I have large substituents here, it actually forces this lone pair to occupy a smaller volume. So it's good enough to say that the bond angle around a nitrogen is 109. Now, something about that bond angle is that molecule is not just stuck in that position with this lone pair here. If it was stuck, then this molecule actually would be chiral here. Now, in fact, this form of the amine is chiral. But what happens is those lone pairs can actually squish out the other side. Imagine grabbing a water balloon at the top, and then all of a sudden the water would squirt out the bottom of the balloon, and then you grab the bottom of the balloon and the water would squirt up to the top. And so these lone pairs are flipping back and forth in an umbrella-like inversion. And it actually goes through this transition state here that actually is an sp2-like transition state. And then you'll invert to the other ones. So these molecules, if we could freeze them, would actually be chiral, but they flip back and forth. And so we say they're not optically active because they actually exist in both the R and the S form. So again, let's say that you're working at absolute zero and you spend a day and you isolate this molecule, the R-ethylmethylamine. And then you start getting super cold, so you take your sample outside to warm up, and you just lost your day's work because now that molecule has established an equilibrium between the R and the S form. So it has what we refer to as a very low barrier to inversion. And so the molecule actually inverts back and forth. So amines typically are not what we say optically active because of this inversion. Now, there are some cases where we can get amines to be chiral. Now, this in the top right-hand corner is a chiral amine. Now, we're not chiral at the nitrogen center, we're chiral at a carbon center. So we can't have chiral amines, so we got to be careful when we say amines aren't chiral. We can't have chiral amines, like in this case here, it's just not chiral at the nitrogen, it's chiral at a carbon, and that's a fixed carbon right there, so it's not going to invert. Now we can have, excuse me, chiral nitrogens. They tend to be quaternary, so they're not chiral amines, they're quaternary ammonium salts. So again, if we protonate or we add an alkyl group onto that nitrogen, we can actually get two chiral forms, the R and the S, and they can actually be resolved, meaning they can be separated. And then in some cases, like these down here, these are really interesting molecules. You can actually constrain the nitrogen in a three-membered ring, and it actually can't invert because it'd have to go through an sp2-like transition state. And sp2 nitrogens want bond angles of 120. And so if that was to invert, it would have to go through that transition state with a bond angle of 120. And as we know, triangles have bonds of 60. And so we just can't get this molecule to invert. So we can actually get these chiral amines. They're actually stuck in this form, and it's due to the fact that they just can't undergo this inversion due to the constraints of that three-membered ring. So in short, amines tend not to be considered chiral, even though one of their forms can be considered chiral. So it's more proper to say that they're not optically active because they can invert. But again, we can't have chiral amines if we're chiral at a carbon center. And in some special cases, we can have chiral amines where they can't invert. And we can also have chiral nitrogens. These are very easy to get. They just tend to be not amines, they tend to be ammoniums. So some other properties of amines. So typically amines with 5 or fewer carbons are soluble in water. And the question is why? And that answer has to do also with this trend that we see on the next line down when we want to explain the boiling points below. So if we just have a molecule that's got 3 heavy atoms here, this is propane, it's got a boiling point of -42 degrees Celsius. If we replace one of those carbons with an amine, the boiling point jumps up significantly to 17. But if we replace it with an OH, the boiling point jumps up even more to 78. So let's answer this question first. Why is the alcohol, why does it have the highest boiling point? You should be screaming at the screen that it's due to hydrogen bonding. So question is, well, why does this ethylamine have a higher boiling point than propane? And you should be screaming the same answer, hydrogen bonding. So amines with fewer than 5 carbons are typically soluble in water. Why? Yes, the answer is hydrogen bonding. And so we can see something interesting down here. We have propylamine that has a boiling point of 50 degrees Celsius. If we just rearrange those carbons, so we still have the same formula, these would just be constitutional isomers. The boiling point here for ethylmethylamine drops down to 34, and the boiling point for triethylamine drops down to 3. Again, these are, all 3 of these are constitutional isomers, have the exact same formula. And so the question is, well, why does the boiling point decrease as we go down here? And again, the answer is due to decreased hydrogen bonding. So for primary amines, we actually have multiple hydrogen bonding sites. So a primary amine, you actually have 2 sites that can form a hydrogen bond, and you have 1 nitrogen that can then form a hydrogen bond with another amine. So you can get lots of hydrogen bonding. But the question is, well, if I can get more hydrogen bonding, why doesn't the amine have a higher boiling point? And the answer to that is that oxygen is more electronegative, and so it pulls away the electrons from that hydrogen a lot more. So when it forms hydrogen bonds, those tend to be a lot stronger hydrogen bonds than in the amine. The amine, being less electronegative, only makes slightly positive nitrogens there. We should understand that because we know that the H off of an alcohol is much more acidic than the H off of an amine. So those H's off of alcohols are much more electron deficient, and so they tend to form stronger hydrogen bonds. And so the answer to why we see this trend down here at the bottom is, well, we decrease the number of hydrogen bonding sites as we change out these hydrogens for carbons. We still got a lone pair on all three of these, but we reduce the number of sites. We go from 2 hydrogen bond donors to 1 hydrogen bond donor to no hydrogen bond donors. Or sorry, yeah, let me change that, sorry, hydrogen bond acceptors. We got 2 hydrogen bond acceptors, 1 hydrogen bond acceptor, and no hydrogen bond acceptors in the last example. Each one of these has 1 hydrogen bond donor, that lone pair right there. But notice this last one actually doesn't have any hydrogens to accept a hydrogen bond there. And so that's why its boiling point is so low. So typically amines less than 5 carbons, so 5 carbons or less, tend to be soluble in water. And so all amines accept hydrogen bonds from water and alcohol. So if we branch them, it does increase the solubility. Some other properties. Most amines smell like fish or rotting fish. So that fishy smell actually comes from amines. So thiols smell like skunk and amines smell like fish. In fact, there's several other naturally occurring amines. I'll let you figure out where these come from that have characteristic smells. But when things tend to rot and putrefy, bacteria tend to produce this diamine here, which is known as cadaverine, as well as this diamine right here that is known as putrescine. And you could probably imagine what those smell like. They smell like rotting organisms. So amines have very characteristic smells. Okay, we're going to cover the basicity of amines, and then we'll call it a lecture. So amines have lone pairs, and so they can act as bases or nucleophiles. So in the presence of an acid, those electrons tend to donate and pull a proton off and end up with salt. So when we want to look at the basicity of a molecule, it's often easier to look at the conjugate acid pKa. And so the conjugate acid pKa, I'll draw it up here, would actually be for NH4 plus, CH3, NH3 plus, CH3, CH2, NH3 plus, and then CH3, CH2, CH2, NH3 plus. And then the question is, which one of these is a stronger acid? Well, the stronger acid would be this one right here. So what does that mean about it as a conjugate, its conjugate base? So this is the weakest base because it is the strongest acid. And then the one on the far right is the weakest acid because it has the highest pKa. So therefore it is the strongest base. So let's see if we can figure out why propylamine would actually be a stronger base than just ammonia. And I'll give you a hint. To be a base, you want electrons. You want things to push electrons into that nitrogen so that nitrogen can push its electrons out. So propylamine is a stronger base than ammonia. And the answer to that is it has induction from these carbons. We're pushing electrons towards that nitrogen, and that makes a nitrogen a stronger base. So for acids, to make an acid strong, you want to pull electrons away from that H. To make a base strong, you want to push electrons towards the site that has electrons. It's like triethylamine has 3 ethyls donating electrons by induction into that nitrogen. And so it ends up being a very decent base that can deprotonate a carboxylic acid, and we actually produce this conjugate acid. If you notice, this conjugate acid is a weaker acid than propylamine. And since it's a weaker acid, the conjugate base should be stronger. So on this page here, triethylamine would be the strongest base. So again, to make a base strong, we want to push electrons into it. And so you can see some of these bases here. Again, how they look at it is they look at the pKa of the conjugate acid. So let me write this down here. Lower pKa equals stronger acid. Higher pKa equals, no surprise, stronger conjugate base. So if you looked on here and you wanted to find the strongest acid, now this guy right here, they're actually looking at this methylamine right here. They're actually looking at it not in its protonated form. So if we look at this guy right there, the pK is 40. So it's very difficult to pull a hydrogen off of just an amine. But if you notice here, this aniline ion, that's as acidic as a carboxylic acid. So that means it's very acidic, and it's going to be a weaker base, stronger acid, weaker base. So on this page here, aniline is actually a weak base compared to any of these other amines. And so the question is why? Why is this a weak base? I just mentioned if we push electrons into the nitrogen, that should make it much more basic. So this actually has resonance that can pull electrons out, and so that makes it less basic. And so you can see down at the bottom here, we have just several different cyclic amines. Again, they're all protonated, so we're all looking at the conjugate acid, or we're looking at the acid here, so we can actually identify which one's the stronger base. So I'll give you a second to see if you can identify among these cyclic bases along the bottom, which one is actually the stronger base. And the key to do that is to find the weakest acid. So this has the highest pKa, that's the weakest acid, which means that in its deprotonated form, this molecule here would actually be the strongest base out of all of these along the bottom. And the weakest base would be morpholine. This is not morphine, this is morpholine. And so that would actually be the weakest base, and hopefully you can understand why. It's due to the inductive withdrawal of the lone pair on that nitrogen by the oxygen. So if we look at aromatic bases, those nitrogens there, We already said that they're not very good bases due to the ability to resonate into the ring. So they're fairly poor bases, but we can actually make them better by putting electron donating groups. So what we're going to do is append a group here. And if we put electron donating groups, that's going to push electrons in and make it less likely for the electrons from the amine to resonate in. So if we push electrons in, that should make a stronger base. So if you notice over here, we get a stronger base when we have electron donating groups on the ring. These two donate by resonance, and this donates by induction. Now we can make the base weaker by adding groups that pull electrons out. So if they pull electrons out, then the amine, the anilin's more likely to donate its electrons into the ring. And so, in fact, what's really interesting is this guy down here at the bottom. It's actually a fairly acidic molecule. Much more acidic than a carboxylic acid. So if we put an NO2 on there, we can actually start to make very acidic molecules. Not quite what we would consider a strong acid yet, but remember the pK of a carboxylic acid is around 5. So this is 10,000 times more acidic than just a regular carboxylic acid. So again, if we push electrons towards a nitrogen, it makes it more basic. If we pull electrons away, it makes it less basic. It's all about the lone pairs. And again, a base is something that has lone pairs and is willing to donate those. So we'll end it there. We'll start off on the next lecture talking about the preparation of amines. And I'll give you a hint, the vast majority of that is review.